All right. Let's pick up where we left off last time. We were talking about these carboxylic acid derivatives. We're going to start talking about reactions of these carboxylic acid derivatives. All right, but first we're going to kind of focus on the namesake of the group. How do we prepare carboxylic acids? All right, this is kind of be a review. We're going to learn a few different ways of converting other carboxylic acids into carboxylic acids, but this is a review of the ways that we've covered thus far. All right, the first class of reactions that we could use are these oxidation reactions. All right, if we take an alcohol, for example, remember our oxidation agents, we had two classes for. And if we had a strong oxidizing agent, like our sodium dichromate with some sulfuric acid and water, this will fully oxidize that primary alcohol into a carboxylic acid. Okay, so oxidation of an alcohol, specifically a primary alcohol, if we're looking for a carboxylic acid. Okay, what other functional group could I have started out with instead that would have given me that exact same molecule? Same oxidation reaction, giving me this carboxylic acid. What else could I have started out with? An aldehyde, right? Something that was already one step oxidized. So if I take this same 3-carbon alcohol, but instead make it an aldehyde, that's already well on its way to being fully reduced to that carboxylic acid. All right, there was one other method that we had learned previously, and that was starting out with those nitriles. Okay, this just required some acid and heat in order to create our carboxylic acid. Okay, so these are these methods that we had learned to prepare carboxylic acids in our previous chapters. All right, there's another reagent that we could use. We haven't seen this reaction before, but it pretty closely follows what we have seen before, is those Grignard reagents. Right, we know that these Grignard reagents, the MgBr, they can react with aldehydes or ketones. So let's just do simply formaldehyde. All right, everybody take a second and give me the product of these Grignard reactions. that nucleophilic carbon of my Grignard is going to react to create a new carbon-carbon bond. All right, and when we talked about these reactions previously, okay, just to keep my color coding consistent, I have my nucleophilic carbon bound to my electrophilic carbon. This is a way to create alcohols. All right, well, we said we don't want an alcohol, we want a carboxylic acid. All right, well, we can take our same Grignard here and react it instead of an aldehyde or ketone. We're going to take, what's this molecule? Carbon dioxide, right? Technically not even an aldehyde because it doesn't have any hydrogens. It's not an organic molecule. Nonetheless, this will react in the same way. We still have our carbon with that oxygen double bond, so it's stealing a bunch of electrons. All right, so everybody, let's see what our, take a second and see if you can't fill in the mechanism for this reaction here. Alright, so I need to start my arrow at a pair of electrons and end it at that electrophilic carbon. I can't stop there. Carbon's going to have too many bonds, so we're going to need to break one of those carbon-oxygen pi bonds. So now I have my new carbon-carbon bond. All right, I still got one of those carbon-oxygen double bonds, but now the other one, that oxygen has accepted that pair of electrons and has this negative charge. All right, these are what we call carboxylate ions. Right, just deprotonated carboxylic acids. Going back to this first semester, one of the first chapters you would have done was to review acids and bases in the context of organic chemistry. And we know that this thing likes to, rather carboxylic acids are considered acids because they like to donate protons, because these carboxylate ions are fairly stable, right? It can lose that proton without messing up its stability too much, in part because this negative charge can be passed between these two oxygens, right? So that negative charge is stabilized through resonance. So these are our deprotonated carboxylates. For being good, we always have that second step where we follow it up with that acidic workup. I should have included that up here as well. And so that's how we can get our protonated carboxylate ion or carboxylic acid. Right, so our last step here would be that aqueous acid. And we protonate that carboxylate ion, giving us our carboxylic acid. All right, and let's just take special note of our number of carbons here. This is a way of creating a carboxylic acid where I've added an additional carbon to my Grignard, right? I have one extra carbon from what I started out with because of that new bond to that carbon from carbon dioxide. Okay, so we can use Grignards to create carboxylic acids as well if we react them with carbon dioxide. Cool. All right, so how do we prepare carboxylic acids? All right, we can use a Grignard or our oxidation reactions to do it. Now we're going to talk about our, and I guess if we just want to summarize this reaction real quick into kind of that more general form, we have our Grignard plus carbon dioxide, and then our acidic workup. We get that R group on there, plus an extra carbon. That COOH is the shorthand condensed form that we use for a carboxylic acid. Right, and again, we just want to make note, we do have that extra carbon added onto our R group. Cool. All right, now we're going to look at our carboxylic acid derivatives. But what we're going to do is we're going to rank them. All right, what we call our reactivity of carboxylic acid derivatives. All right, and we're going to rank them from the most reactive to the least reactive. All right, so we're going to put all those carboxylic acid derivatives on this reactivity scale here. All right, so the most reactive are those acyl halides. All right, what I'm going to do is kind of stagger these in a line here. I'm also going to take this opportunity to introduce two more that we don't have to know the name nomenclature for, all right? So I didn't introduce them with the previous batch where we learned how to name them. These are ones that we just have to recognize as functional groups. All right, the next one is what's called an acid anhydride. Also a very reactive carboxylic acid derivative where you have these two carbonyls linked with this oxygen in between. All right, and these are what are called acid anhydrides. Okay, the next one down the line is what we call a thioester. Kind of like an ester, but instead of having an ester oxygen, you have an ester sulfur, a thioester. All right, next down the line here, we actually got a tie between our carboxylic acids, just the regular old carboxylic acid, and if we keep that same oxygen there, but replace that hydrogen with an alkyl group, we call that instead an ester. Those are tied on my reactivity series here. All right, and the last one, our least reactive carboxylic acid derivative, is that amide. All right, so our ranking from most reactive at the top to least reactive down at the bottom. We took all those carboxylic acid derivatives and we ranked them. Okay, again, our carboxylic acid and our ester are tied. They're tied at the same place in this reactivity series. The most is an acyl halide, followed by an acid anhydride, a thioester, then that tie between carboxylic acids and esters, and finally the least reactive in our series here being that amide. Okay, so why did we bother ranking these on this little scale here? What we're going to see is that we can freely convert from something more reactive to something less reactive. But we can't go the other direction. At least not without a fancy reagent. We are going to learn about one way to go backwards here. All right, so first of all, let's convince ourselves real quick, or rather, let's just show that we can convert something that's more reactive into something that's less reactive. All right, so we're going to convert this acyl halide into this acid anhydride. So we're going to take that acyl halide. We'll use this acetyl chloride here. Okay, and what are we going to react it with in order to convert it into an acid anhydride? Well, look what we need to add on to that molecule, right? We need to substitute our chlorine here for this group over here. And so that's what we're going to use. Okay, a carboxylate ion. All right, so which one of these do we think is going to play the role of our nucleophile, our electron-rich species? The carboxylate or the acyl halide? What do we think?
Carboxylate.
The carboxylate. We got a bunch of electron density here. Cool, so this is going to be our nucleophile. And what about our lack of electron density, our electrophile? Where's the electrophilic site on this molecule? That electrophilic, carbonyl carbon. All right, so what's going to be the first step in our mechanism? We have that high electron density nucleophile that's going to attack that low electron density electrophile. All right, and I can't just stop with that one arrow. What else am I going to have to do?
Leaving out.
We got to have that pi pair of electrons jump onto our oxygen, our built-in leaving group. And this is going to create this intermediate. We've given it a name before based on its geometry. Our tetrahedral intermediate. All right, we have this new bond between our nucleophile and our electrophile. All right, I said those backwards, but nucleophile and electrophile. All right. We have this tetrahedral intermediate here, okay? And this is going to be the key difference between what we saw for aldehydes and ketones versus what we're going to see in this chapter here. Previously, when we got to our tetrahedral intermediate, we looked at it and we said, all right, well, we don't have a good leaving group on there, so we're stuck until we protonate that alkoxide oxygen. All right, well, this does have a good leaving group. My chloride here is a great leaving group. Weak base, super stable with that extra pair of electrons. So this alkoxide ion, not super happy to have this negative charge. It's going to bring that negative charge back down and kick off that leaving group. The chloride is more stable at holding a negative charge than my oxide ion is here, my alkoxide ion is here. So that pair of electrons comes back down, kicks off that chloride leaving group, and that's how we get our acid anhydride. Alright, and just to keep my coloring consistent here, we have this new bond between our carbonyl carbon and that oxygen of our acid anhydride. And chlorine in this molecule was playing the role of that leaving group. So we said we could convert something more reactive into something less reactive, and so what we showed is we converted this acyl halide into this acid anhydride. All right, now let's try to ask ourselves, let's explain this reactivity series. Right? Why is that acyl halide more reactive than, let's say, an ester? well, let's look at this chemical equation here. We're going to take that acyl halide and react it with this methoxide ion here. All right. This creates that ester and that chloride ion. All right. So first of all, this reaction here, according to what we just discussed, which way does it go? In the forward direction or in the reverse direction? In the forward direction. We're going to create, convert something more reactive to something less reactive, right? But why? Okay, well, let's take a look at our intermediate here, right? That tetrahedral intermediate. So everybody kick off this reaction here. Show our reaction mechanism. That alkoxide's going to attack that electrophilic carbonyl carbon, kick that pair of electrons up. We got that world famous tetrahedral intermediate. We would get the exact same intermediate if this reaction went in the reverse direction though, right? If my chloride ion instead did the attacking, I would then form this same tetrahedral intermediate. So looking at this intermediate here, why does this reaction proceed in this direction as opposed to in this direction? Exactly, right? Because the chloride is a better leaving group. And that's the key here. That's the entire key to this reactivity series. Really what we've ranked here is in order from best leaving group to worst leaving group. Kicking off that nitrogen, much harder to do. Nitrogen hates having a negative charge, right? Oxygen, it'll do it, but it's not super happy. You can stabilize it through resonance, but the only one that's really super stable with that negative charge is that halogen, right? And so that's explaining our reactivity series here. Why can we convert something more reactive into something less reactive? Because more reactive implies a better leaving group. Oops. All right, this tetrahedral intermediate forms here. This oxygen, not super happy to have this negative charge, would rather not, right? So which one of these two is going to get kicked off? Well, my chloride is a much better leaving group than this alkoxide ion, also pretty angry to have that negative charge. right? So that's why this reaction here proceeds in this forward direction as opposed to the reverse direction. All right. So we can convert our acyl halide into any of these other carboxylic acid derivatives. All right, I know, super cool. That means that they're by far the best starting point for a synthesis reaction, right? Have the most flexibility here. Okay, so for our acid anhydride conversion, we said that we needed to use that carboxylate ion. This is the one where you actually do have to use a carboxylate ion, a carboxylic acid. The protonated version of this, the neutral form of this nucleophile, is just too crappy as a nucleophile to actually work. For these other ones, though, we can actually use our neutral form of our molecule. So in order to turn an acyl halide into a thioester, I just need this in its neutral nucleophile form, or thiol. What would I use to convert an acyl halide into a carboxylic acid? What nucleophile would I use? If I'm trying to replace this with this, what am I going to use? So you could use hydroxide, that would definitely work, but you could even use just the neutral form of that nucleophile, or water. Right? Likewise, if you were going to use an acyl halide, you could use those alkoxide ions. They tend to be kind of expensive, so why would you do that if you could just use an alcohol? All right, or we can use our ammonia to make our, in this case, primary amide. You could use an amine to create a secondary amide. All right, we are going to note here that because these amines / ammonia are good bases, and there's this proton transfer step that occurs, you're going to have to use two equivalents of ammonia. One of them is going to get consumed as a nucleophile, the other equivalent gets consumed as a base. And as soon as it becomes that protonated form of the amine, it can no longer be a nucleophile. It's got a positive charge associated with it, no lone pairs to donate, so that's why we're going to need two equivalents. All right, we can play this same game over and over again, and it's going to look really similar. We can also convert an acid anhydride into that thioester. And what are we going to use? A thiol. Right, so we can go ahead and fill out this little cheat sheet here. It's going to look pretty repetitive. How would I turn an acid anhydride into a carboxylic acid? I would use water. How would I turn it into an ester? I would use an alcohol or an amide, two equivalents of ammonia. All right. My thioester, same game, can convert that into a carboxylic acid, an ester, or an amide. By adding water, an alcohol, or two equivalents of an amine. right, so again, we can convert something more reactive into something less reactive by adding in that proper nucleophile to do our conversion. All right, when we get to this row here, though, we're going to have to talk a little bit more special. All right, it turns out that your ester can be converted into an amide exactly as you would expect by adding those two equivalents of NH3. All right, but it does not work for a carboxylic acid. All right, that path does not happen. You can just kind of maybe show that. Okay, so why is that? Let's think here. Let's go ahead and test this out. We're just going to let's do what we would expect based on this trend that we've seen for everything else here. We got our carboxylic acid and our amine. Let's just do a primary amine for fun here. And we're saying that this does not form our expected amide. An N-ethyl amide here. Okay? And that's because another reaction happens much more favorably and much more quickly. Does anybody know what that reaction would be? Between a carboxylic acid and an amine, our good organic base, carboxylic acid, base, yes, an acid-base reaction, a neutralization reaction, yes. So instead, that nitrogen, yeah, that nitrogen's a good nucleophile, but it's not going to attack this tucked away carbonyl carbon here. It's going to really quickly just deprotonate that carboxylic acid. All right. Okay. And the problem here is this carboxylate is not an electrophile. Now I've got a bunch of electron density bouncing around between these two oxygens here. So this carbonyl carbon is no longer electrophilic. It's got quite a bit of electron density, all right? Likewise, my nitrogen, whereas an amine has that lone pair and can play the role of an electrophile, an aminium ion, this protonated nitrogen, cannot. So this is not a nucleophile. So because of that acid-base reaction, that proton transfer reaction, all right, we will not get our expected substitution product here, our new carboxylic acid derivative. Instead, we will get, you can certainly react these with one another. You're just going to get a carboxylate ion and an aminium ion, right? A protonated amine. All right, and you're just kind of crushed on two fronts because not only is this faster, but it's also more energetically favorable. Cool. So there is one way that we can go backwards here, right? Great. If we start out with something more reactive, we can get to something less reactive. But, man, we would really like to get to this most reactive thing because that gives us the most flexibility. So we have one way of going backwards on this path here. And this is using a familiar reagent that we've seen before. Thionyl chloride. So now we're going to create an acyl halide, or prepare, I guess, an acyl halide. All right, so let's just remind everybody we've seen this thionyl chloride before, SOCl2, when we were talking about alcohols, and this would convert this alcohol into what? One propanol will become one chloropropane. Holy cow. All right, well, it turns out that if instead of starting with an alcohol, we started with an carboxylic acid and treated that with that thionyl chloride, it actually does the exact same thing. It substitutes out that hydroxyl group for a halogen, but if we start with a carboxylic acid, that means that we would be ending with that acyl halide. All right, so this is our one way of going backwards from something less reactive to something more reactive. We required this fancy reagent here, thionyl chloride, right? But we can go backwards on our little cheat sheet here, starting with that carboxylic acid. Go back to our acyl halide here, using that thionyl chloride. SOCl2. Cool. All right, we're going to leave it there. Next class period, we've kind of glossed over these two equal ones here. They are equal because you can freely convert one to the other and back again, and we'll pick up with that next class period.